Okay, hey everybody, welcome back to chemistry. First class of the week, late on a Sunday afternoon, so I won't go too crazy. Typical fashion, we'll probably finish this section. This section will be a little bit heavier than previous sections, like in chapter 1. We're really getting into some math now, and then if I have time, I might introduce the next section. But today we'll finish this concept of calorimetry. Some of you guys did I guess anybody who was in the lab last week looked at this, and this information should help you a little more in your labs this week. So just a quick review. Calorimetry is the measure of heat in a system, keyword system. Now, and we'll talk a little bit more about this today. When you make your measurements in chemistry, the thermometer is, and again, I'll talk a lot about this today. So if you're confused, just kind of give me today's class. But when you make a measurement in chemistry, your goal is to study the system, the chemical reaction. But what your thermometer is actually measuring is the surroundings. It could be the water around the chemical reaction. It could be the air outside the chemical reaction. Like for example, I have a good example of the difference here. If I go back to the bomb calorimeter, okay, the temperature that I'm measuring, let me see. Okay, good. I was having issues writing on my slide, but it's working well now. This is the surroundings. This is your system. So when we use in math, or sorry, in chemistry, the formula MC delta T or MCT, or sorry, C delta T, sorry. It won't let me erase. Q is C delta T, which you won't really need in this course because this is specifically for the bomb. But when we use Q equals MC delta T, we're actually finding the heat of the surroundings. And your goal is to find the heat of the system. So we're going to talk about this today. All right. So let me kind of go back to my notes here. We did this example on Thursday. If you were not here on Thursday, you didn't miss too much. We only looked at this one example. So I won't do the example again. I have many more examples, as you can see. But I'll just quickly remind you that the formula for calorimetry in this course is Q equals MC delta T. Q is MC delta T. For some reason, my pen isn't letting me write on the screen, but oh well, I'll figure it out. So Q meaning heat, M meaning the mass of the surroundings, like the mass of what your thermometer is in. Delta T would be your change in temperature. It's always T final minus T initial, T2 minus T1. And then C is your specific heat capacity. When you're dealing with an aqueous solution, we typically assume that the specific heat capacity is the same as water. Okay, you'll see a little different example here at the end of this class. I have a very tricky practice problem at the end of this class for you. But typically, when we're dealing with solutions, C is the heat capacity of water. It's an assumption that we make because most chemical reactions are in aqueous solutions. And as Aman just said in the chat, yes, this is definitely in the data booklet. This will be kind of like your magic number for C, especially on like a test or something like that. Again, I do have a challenging practice problem at the end of today, but most times your C will be 4.184. So guys, I'm not going to go over this practice problem again. We did this on Thursday. I'm going to skip ahead to the next one, and we'll start from scratch. We'll do this one together. And actually, just give me 1 second here. Sorry, I meant to do that. My PowerPoint isn't letting me draw on it for some reason. My pen isn't acting like a pen. Hold on. Technical difficulties. Give me 1 second. I don't know if this is going to work. Okay, no big deal. I have a way around my problem. Sorry. Okay, so this is a good example. This is what we'll start with today. 1.95 grams of potassium nitrate is dissolved in 50.5 or 50.5 grams of water. So this is obviously an aqueous solution, meaning we're going to assume the heat capacity is 4.184. Now, guys, I usually make your tests. I promise you, I will typically put this here. Okay, so this will be here written for you. Iman asked, do we need the data booklet? I mean, it's a good data booklet to have, but honestly, I typically will put this right in the question so you don't have to worry about what C is. Okay, so this is an aqueous solution, which means it's dissolved in water. We're going to assume C is the same as water. So both chemicals start at 20 degrees Celsius, and once we mix the chemicals together, they reach a final temperature of 32.1 degrees Celsius. And the question is, what is the heat, Q? mc delta T. Now, there's one exception, or not exception, but trick to this problem. The mass, okay, so I'm looking for, let me clear my drawings here. I'm looking for the heat, Q, in the entire solution. And this is where a lot of you guys are going to lose half of a mark on a test or something like that. This is a really, if you guys want full marks, 5 out of 5 or 4 out of 4, you have to be careful. I want the heat of the entire solution. So the question is, what is the mass of the solution? What is the heat capacity of the solution? And what is the change of temperature of the entire solution? Now, what a lot of students will do is they will only take the mass of like the chemical. You know, the minute you guys, your brain sees KMNO4, you're like, oh, there's our mass. But I want you to give me the heat of the entire solution. Okay, and that sample is dissolved in water. So this mass, let me see if I can pick a different color here. I'm feeling green today. This mass has to be the total mass. It's the mass of the solution, the entire thing. Okay, so Q is M. I add up my masses together, multiplied by C, which I have written here, multiplied by delta T. Now, this is another place that students can get messed up, is which is T2 and which is T1. Remember, delta T is always T2 minus T1, or what we would say the final temperature minus the initial. So what's the final? What's the initial? Well, this is where your question comprehension needs to come into play. You need to read this carefully. Both chemicals start at a temperature of 20 degrees Celsius. Okay, so that's obviously T1. That's the initial. That's where they start. And they finish at a final temperature of 32.1. So pretty easy question, isn't it? I just subtract my numbers, or subtract my temperatures and multiply by my mass and my heat capacity. So here, Q would be positive 2.66 kilojoules. I'm rounding up. I would be careful in your labs with your calculations. Like I'd watch out for significant figures in your labs, but for your tests and things, I won't really be too concerned with significant figures as long as your answer is close. Oh, I'm getting some good chat in there. Yeah, so yeah, so like Abdul Halim, you talk about the mass. We use the total mass. Iman mentions heat as a type of energy. That's why we use joule or kilojoules. Yep. Heat is a form of energy. It's kind of like it's the type of energy of heat. Heat is a transfer of energy from something hot to something cold. You can think of it as mechanical in the sense that molecules collisions control heat, but I wouldn't get too worried about it for this course. And so Aman, that's a good question. So the last question in the chat is really good. Do we need to mention the sign if it's negative or positive? Well, just like in math class, if the sign is positive, which it is here, yeah, I don't really need to see it. It's up to you. But if the sign is negative, you must include it. So you must include negative sign if it's there. Now, how will you know if it's positive or negative? The math does it for you. So trust your calculators. The T final minus T initial will tell you the sign of Q. Okay, so trust your calculators. You're not expected to know if it's positive or negative. The math will tell you. So if your calculator says negative, make sure you put it there. Yep, you can ask away or ask your question away. I think I might know what it is. Oh, okay. I got another question. I got two questions. This is giving me flashbacks of last year in 1120s. I have lots of questions, which is good. So let me answer Yasmin's question first. Is this exo or endo? That's a really good question. Because the sign is, well, here's the thing. We're not really ready to answer this yet. But the idea is this would be an exothermic reaction, but you might be confused right now about why that's exo. We're not ready for that yet. I'm going to teach that on the next few slides. But because the temperature goes up, this would be exothermic, meaning it releases heat. And again, some of you might be thinking, whoa, the sign is positive. That doesn't make sense. We're not there yet. I'm slowly working towards it. Trust me. But because the temperature goes up, this is exo. Yeah. Hadil asks about the sig fig rules. Again, I would follow sig fig rules on all of your labs. I wouldn't worry about it on your test. And then Aman's question, I have another question about endo or exo. I'll get there. We're not ready for that yet. And then Aman's question, if you have cold water and hot water with the same amount of water and we mix them together, which will defeat the other? That's a good question. Okay, so I won't spend too much detail on this question, but it is a good question. If cold water and hot water with the same amount are mixed, which will kind of defeat the other? And the answer to that question is it depends on how cold the cold water is and how hot the hot water is. Without knowing the temperatures of the water, you can't answer that question. But like if you had 100 grams of water at -10 and 100 grams of water at +10, and you mix them, they would briefly reach equilibrium at 0. Okay, it really depends on the temperatures. If you had 100 grams at 0 and 100 grams at 100, again, it might equilibrate around 50, but that depends on phase changes. I mean, that's a really complex question. So it's a good one, but you need a lot more information. All right, let's do another one. And this might explain the whole endo and exo thing. Actually, hold on, let me see. Yeah. Okay, cool. Okay, another example. Now this one's a little tricky. So 20 grams of aluminum is heated to 150 degrees Celsius. It is dropped into a container of water, and that mixture gets a final temperature of 32 degrees Celsius. How much heat did the aluminum lose? How much heat did that aluminum lose? Okay, so sorry, I'm just checking something out. Sorry, give me 1 second here. Okay. Sorry, this question was kind of missing a piece of information. I had to check with part C there. That's fine. Okay, so let's go through this one, and then I'll give you guys one to practice yourself. Okay, 20 grams of aluminum It's heated to 150 degrees Celsius. And I'm given the heat capacity of aluminum right here. Now, notice that our system right now is aluminum. So I can't use water. I'm using a pure metal. Okay, so 20 grams of aluminum, it's heated to 150 and it's given a heat capacity. It's dropped into a container of water and that mixture has a final temperature of 32.1. So how much temperature, now keyword, sorry, not temperature, how much heat did the aluminum lose? Or if you had a British instructor, he might say aluminium. How much heat did the aluminium lose? Okay, I'm asking you about aluminum. So that means you're going to use the mass of aluminum, you're going to use the heat capacity of aluminum, and then of course delta T is as normal, final minus initial. The reason that that's important is I'm asking you for the heat of the aluminum. This does not form a solution. I'm dropping a solid chunk of metal into some water. So to find the heat of aluminum, you can use little subscripts here if you want to. Okay, I'm going to take the mass of aluminum, the heat capacity of aluminum, and the delta T. Now, the delta T, be careful, it's final minus initial. So this is T2, this is T1. It starts, the aluminum starts at 150 degrees Celsius and ends at 32 degrees Celsius. And what that's going to do is give us a negative number down here. So I take, again, my mass of aluminum, 20 grams, my heat capacity of aluminum, and then I do multiply it by my change in temperature, final minus initial, and I get my answer. The aluminum has lost 212 joules of heat, 212 joules. Okay, now I got some stuff going on in the chat. Let me have a look. Yeah, okay, so I'm getting some good questions here. Oh my gosh, I'm getting crazy questions. So Iman, like how long does a student need to survive in the cold ocean? Again, that depends on the temperature of the water. And you can look that up, like there's studies on humans and hypothermia is what it's called. So how long could a person survive in like -10, -20 water? I don't have the answer to that. That's biology, but you could certainly find that information online. You know, if you I think they say, you know, if you fell into a freezing cold lake in like Canada, you might only have so long amount of time to survive, but I don't know the answer to that. Now, Abdul Halim in the chat asked the question that I thought most people would ask. What about the mass of water? Why are you ignoring it? And that's a really important question. So yeah, Iman, cold can definitely kill a person by swimming. And it would be hypothermia, yeah. But anyways, Abdul Halim, I think I said your name right. You asked the question that I was hoping someone would ask. How come? What is going on here? Why did I add the masses in? My computer is not being my friend today. Why did I add the masses in this example? And then why didn't I add any mass of water in this example? Now, I know there's no mass given to you, but that's not the point. Why didn't I care about the water? And the key is it's about what the question is asking. So this question here, guys, oops. It's got to be a Sunday because my computer is like, just like, nope. The key here, guys, is this question is asking for the heat of the entire solution. Remember chemistry 1121. A solution is when two chemicals mix to form a homogeneous solution, homogeneous, homogeneous. So when I put my thermometer in here, I can't measure just the KMNO4 or just the water. I'm measuring the entire solution. So this means, because I'm looking for Q solution, that means I'm also going to use the mass of my solution, the heat capacity of my solution, and of course, delta T doesn't really change. So if you're wondering, how come in this example, I used the mass of the water and the chemical? It's because I'm looking for the heat of the solution. Why did I use 4.184? Because that's the heat capacity of the solution. Okay, now go to the next example. How come in this example, I only use the mass of aluminum? Now, obviously, there's not even a mass of water here, so I couldn't even add it if I wanted to. But the key here is the question is asking for how much heat did the aluminum lose? So I'm looking for the heat of the aluminum, which means I'm going to use the mass of the aluminum. It doesn't say solution, it just says aluminum. And I'm going to use the heat capacity of aluminum. And then, of course, delta T stays the same. So when you do these questions, be careful. If it says solution, you need to add up the mass of the entire solution. If it just says, what's the heat of aluminum? What's the heat of iron? Just use that metal. Yeah, so thank you, Abdul Halim. And I didn't mean to explain that too long for you. I meant that for everybody because that's such an important question. Aman mentions the heat equation is with a closed system. Yes. So like, in physics, and I don't know how many of you are in physics, but in physics, when you calculate like the velocity of a bullet or the distance a football will travel, you ignore things like the wind and air resistance. In chemistry, we assume that these are closed systems. Now, this is my favorite part of this question, part B. And guys, wink, wink, wink. This is definitely a question you'll see. You saw it in the lab last week. You'll see it in the lab again this week. So you're going to be doing this again this week with a little twist. This is the easiest mark you'll ever get in a thermochemical question. If the metal, and before I even put my words up, I'm going to draw a little picture here. Or I'm going to try to draw a picture. Technical difficulties. I am by no means an artist, but here's my picture. Okay, so there's my aluminum. That L shouldn't be capitalized, but anyways, I stand by my mistake. If the aluminum lost, what was it? How many grams of, oops, sorry, hold on. Let me just get the number. How many joules did the aluminum lose? So if the aluminum lost I'll figure out my computer someday, 212 joules, which is why it was negative, right? So the reason it was negative is because it was losing 212 joules. My question to you, if the aluminum is my system, how much heat did my water gain? Tell me in the chat. If my aluminum lost 212 joules, how many joules did my water gain? And as Aman said, in a closed system. Thank you, Harold. My drawing, I think it was okay. And yes, everybody in the chat is correct. And Aman says it beautifully. Same number, different sign. I could not have said that any better. And everybody is saying positive 212, 212, 212. That's beautiful. Just going to Aman's question about you can't ignore air, you are correct. And you guys did a lab last week in a coffee cup. There is no way your coffee cup is perfect. You guys are losing heat to the atmosphere. You might lose some solution on the thermometer. Nothing in theoretical chemistry or physics is necessarily perfect, especially in first year. We make a lot of assumptions to make life easier. So you can't ignore things like air in physics. You shouldn't ignore things like open and closed systems in chemistry. But for first year, that's what we do. It just makes life easier. So for those people in the class who are not a fan of my beautiful art, I know Harold was, there's a mathematical way to represent this. And Iman said it beautifully. The system and surroundings have the same number, but they are opposite in sign. Okay, so exact same number, opposite in sign. So my system was losing, my system's my aluminum, my water is my surroundings. My system lost 212 joules, so negative. My surroundings gained. So my surroundings gained 212 joules. Again, I'll talk about the exo or endo in like another topic. I'm going to show you how to figure out if these are endothermic or exothermic, but we'll talk a little bit about that as we get further in this topic. I want to talk about enthalpy first, which I hope I get to today. Well, I hope I introduce it today. And yeah, I mean, Iman is exactly right. It's for every action, there's an opposite and equal reaction. It's the law of conservation of mass, the law of conservation of energy. If that aluminum lost 212 joules, it had to go somewhere. It doesn't vanish, it doesn't disappear. And where it goes is mostly in the water. Again, there's some assumptions there. You know, we ignore the beaker, we ignore the air around the beaker, but you know, this is first year. This is all I ever did. I'm not trying to like rob you of any learning. This is what every first year student does ever. So it just makes life easier for ourselves. You guys got enough stuff to memorize anyways. Now, this is a tricky question. Well, you know, trickier than the last question. Part C. Okay, now we got to put our thinking hats on. If the initial temperature of the water was 20 degrees Celsius or 20.3, how much water was in that beaker? What a cool question. What an interesting question. And if you guys, if you did this in the lab, you could calculate the mass of water. Now, I mean, why would you? You could just weigh it or measure it on a beaker, but you could do this. This is a real question. In order to do part C, we need to make a list of everything we know about the surroundings. So first things first, the Q of the water, which is the Q of the surroundings, same thing, was positive 212 joules. Okay, if you're actually doing this on a calculator, you can leave some extra significant figures, but again, I'm not worried about significant figures. The mass, who knows, right? Well, that's what the question's looking for. Okay, well, what else do we know? Well, we know the heat capacity of water is 4.184. I'm writing real small, but I'm impressed. This is in your data book. If any of you wonders where this number comes from, data book. It's the only one you need to know from your data booklet. Water is our most favorite chemical in the world. Okay, now the challenge here is delta T. Okay, delta T. Delta T is final minus initial. So I know that T1, my initial, was 20.3. So can somebody tell me, I'm going to see, I know it's like 5:05 on a Sunday afternoon. I know it's here, but how did I know that the final temperature was 32 degrees? Where does 32 degrees come from? Where did I get this number I'm writing here? Okay, if you can turn on your mic, you can chat it in the chat. Where did I get 32.1? I did not make it up. It comes from somewhere. Yeah. And Abdul Halim, you're right. This is just math. I mean, I'll explain that in a second. You make a good point. Aman is right. It says that the final temperature, and I'm getting math as well. Yeah. But really, math is where we're getting the answers, but where did 32 come from? And Aman got it perfectly. It says the final temperature was 32. Now, guys, ignore the mess on my screen. I'm having technical difficulties today, which is new. This is a new mistake. My pen is just being rude to me. But it says in part A here in the first question, and I don't really want to underline it, guys, because I have so much writing on my screen, but it says it is dropped into a container of water and the mixture has a final temperature of 32.1. So that final temperature comes from the first question. So you plug those numbers in, type them all in, put them in on your calculator and solve. Now, there is one exception here. I am assuming that you guys are pretty good with math, okay? If you're not, you need to touch up on your math a little bit, but this is your third or second chemistry course. Note that I'm solving for M here. M, if I rearrange this formula, is Q over C delta T. I'm just rearranging this formula. You can rearrange it first using algebra, or you can rearrange it after using the numbers, which is still algebra. But this is the formula I'm using. This is not in your data book. Okay. This is, you guys need to know how to rearrange equations. This is about as hard as your equations ever get. So I moved the C and the delta T over by dividing them. If any of you really have trouble with algebra, you can always make an appointment with me, like send me an email and we can talk about it. But I'm not going to use class time to talk about math, not too much. I do want to go back to what something that you could hold on now. I'll go. There's a few comments, but I do want to go back to something Abdul Halim said about it just being math, and Abdullah said the same thing. Honestly, guys, the minute you identify the system and surroundings, chemistry is over, and it is just math. Which is kind of, you know, as Harold says in the chat, he's not a big fan of the math. This is the challenge. But the good news about Chemistry 1121 is it's a mixture. So not everything is math. There'll be some stuff later in this unit that's theory. Unit 3 has theory. Unit 4 has theory. I'm trying to remember what all the units are. Yeah. So don't worry. And yeah, Aman might have a good point too. I think my pen is getting old. It actually might need a new battery because it's not being my friend here today. Okay, I'm going to do two things before we finish today. Okay, I'm going to clear my writing. This will be put on YouTube. Don't worry, because this is a very tricky class. I'll tell you two things. And then I just want to tell you two things about this, and then I want to do one more thing. This is a very hard problem. This problem, guys, I'll tell you right now, I wouldn't put on a test. This is a challenge. Now, I know if you guys look at your PowerPoints, you can get the answer. Okay, so it is here, unfortunately. I kind of wish it wasn't. If I had my time back, I would have deleted it. But, and I'm not going to ignore this question. We will go over this, but I'm going to leave this question for today. I'd like you guys to kind of let all of this material kind of absorb. You know, think about, you guys are endothermic students and you're going to absorb all of this knowledge. Take all this knowledge and try to do this question without looking at the answer. Oops, sorry. Okay. This, again, I feel is probably a little bit too crazy on a test, but this is a good challenge question. I wish I could draw like an evil face here. There's my evil face. This is a good, hard question. So I'm going to leave that question here. We will go over this question at a later date, maybe when we do review. Maybe I'll do it tomorrow at the beginning of class to see how you all did. But this is not a test question. This is a challenge question. All right. Are you, Iman, are you asking a question about this challenge question or the one before? The challenge. Okay. I don't want to talk about this too much because I do want to do one quick thing. Okay. So Aman, you saved the day. I think you saved the day. Aman asked, why did we ignore the sign in this question? What's going on? I think that's a typo in my notes. That's a good thing. This would be negative. Sorry. Oops. Oh my gosh. I'm gonna spend like 6 hours tonight fixing right. If it's negative here, it's negative here. Aman, really good catch. That's a little typo. So this is part of the challenge. See, even I made a mistake. So it's just a typo. This negative goes here. My bad. Ha. Okay, cool. Finale of today. It's 5:10. I don't want to take up more of your time. Okay, I got another private message. I'll get to that message in a second. I don't want to take up much more of your time. I just want to introduce what we're going to do tomorrow, and then halas, we're finished. Okay, so just give me 5, maybe not even 5 minutes, just a few, like couple minutes. I did get a question in the chat before I do introduce this next topic. I'm not going to do too much today. I'm just going to introduce it to you, just to kind of let you know what's coming up. But I did have a question in the chat, which was a private message, but a good question. It was, if you are interested in my office hours, do you have to write me an email? Typically, no. This semester, I've been just on Zoom, just waiting to see if anybody showed up. I've had a few students show up. If for some reason I'm not there, just send me an email and I can be there really quickly. What happens is if sometimes students don't log in and I'm not active, meaning I'm not like typing or using it, it automatically logs me out and I don't notice, but I will be there. I've been there all this semester. If anybody's wondering, how do you find me in my office hours, it's written here. You go to your course. Okay, I just want to make sure I'm sharing my screen, which I'm obviously not. There we go. So go to your D2L, and here it is here. You can see my office hours, and the link is here. And again, if for some reason you don't see me there, send me an email. I'll get it. It goes right to my phone. The only time I've not been there is if my computer assigns me out or like I'm running a 5 minutes late or something. This link here also includes your playlist. So all of the recorded lectures are there. I've updated it until the 27th. I'll put the rest of your lectures on now shortly after this. Whew. Okay, I guess I ran out of time, didn't I? Well, here we go. Just give me 60 seconds. I'll just introduce what's coming up next and halas. We'll finish. So I'll just keep it like this. I won't make it full screen. In this chapter, we're going to talk about enthalpy, which is something you're going to do in your lab this week. It's very, very easy. If you do have your lab before the next class, you might want to kind of skip ahead and read some of these notes. You can always send me an email, no problem. But if your lab is after the next class, you'll have a little bit better of an idea about enthalpy. Okay, enthalpy is the term we're going to use, and I had this question today. Let's see if my pen works. I bet you it's not. Nope, of course not. I'm gonna cry. No, I'm not. I'm not really gonna cry. But today, when I had a lot of students ask, is it endo or exo? This is really one of the best ways to figure out if a reaction is endo or exo. I'll give you one other hint, and then that's it. If some of you are wondering, how do you know? Hold on. I know I said 60 seconds, but my computer is being a jerk. If I asked you endo versus exo, how to tell, you need to look at the surroundings for temperature. If the temperature of your oops, sorry, I did that backwards. If the temperature of your surroundings goes down, or if the temperature of your surroundings go up, it would be exo. So sorry, endo is temperature goes down. This is your surroundings. Exo is temperature goes up. But there is an easier way to talk about this, and this is if delta H is positive or if delta H is negative, that's another way. We'll talk more about that next class. But for right now, like if you're in the lab and the thermometer temperature goes down, it's endo. If you're in the lab and the thermometer temperature goes up, it's exo. That's a good way to think about it in the lab. In a exam or test or on a, in a question, we would look at what's called enthalpy. And we're going to talk about that in tomorrow's class. Okay, everybody, so that's it for me today. I went a little longer on a Sunday afternoon, but I did have a million very good questions. Your test will be on paper on campus, unless this is a question from Hadil. COVID numbers are going up. Thank you. I pray for my computer too, Harold. But COVID is not going up too crazy, so don't panic or anything. But all I'm saying is, as of today, your tests will be on campus. If something happens with COVID, we'll move them online. But as of right now, they'll be on campus. Okay, which day we're looking at towards the middle of February, but we don't know the day. But it won't be any time it's not this week. Don't worry. Okay, so it won't be this week. It'll be, late next week, middle of February kind of thing. All right, thanks everybody.
Mr. Mark,
Yes.
I have a suggestion.
Yes, sure.
What I saw from my friends
Mm-hmm.
from other classes, they have like they